So tomorrow is test day, and again, this is recording right now, so feel free to review this as many times as you want between now and then, and we'll go ahead and get started on this. I would encourage you to follow along and try and write this stuff down as we go through it together. There are some pieces of blank paper on the table in the back, and it is time to jump in. So the very first thing that we talked about in this chapter was the principle of superposition. So let's say that you've got two waves. Maybe they look like this.
What is this called?
Principle of superposition. And for this question, I'd like you to try and draw what these waves are going to look like when they're in the same position, and then what they're going to look like a little bit after they're in the same position. So right when they're in the same spot, and then what happens after they're in that spot.
Is it provision or position?
Superposition.
Oh.
Yep.
What's the question?
The question is to draw what these waves are going to look like when they are in the same position because they're heading towards each other, and then what are they going to look like after they're in the same position. So what happens when they're done with that?
Oh my gosh. Diffraction. Wait. Physics shirts.
What?
Physics shirts.
That's right. That's not the answer to the question, but
Oh, sorry.
physics shirts are going to be awesome. So no need to apologize. Some more exact change. That's perfect. Let's just put your name in the side of the shirt. So what are these waves going to look like when they're in the same position? One big wave, absolutely. You're just adding whatever this height is to whatever that height is. When they're in the same position, you'll have something much larger. That might be a bit exaggerated, but you get the idea. That's the principle of superposition. Now, what's it going to look like after these waves interact? We've got, the smaller wave and the bigger wave. They're either going to bounce off each other or they're going to pass through each other, and that's really going to determine what this is going to look like. So, what is it going to look like? Yeah, they pass right through each other. So that means this wave is going to be on the left or the right? The left, yeah. Because after they interact, they go right through each other, and after a little bit of time has passed, this is the sort of thing you would see. They're headed in their original directions as though nothing ever happened.
Would it still be the same size?
Yeah, still the same size. Okay. That's the sort of thing you'll deal with on the very first question. And of course, we got to do a few things with maximum lines. So, this is just from worksheet number 4. I want to try and make sure that you're okay with these types of diagrams and different locations on them. So, let's say that I ask you if this spot right here is constructive or destructive interference. Okay, so this one's going to be destructive. That's okay. That's why we do this review session. So, yeah. Yeah, so we've got a crust right here, but it's exactly in between these two crests. And so what that means is you've got a crest and a trough in the same spot. That is destructive interference. Now, what if I put a dot right here? Constructive or destructive? Constructive. Because what do we have? 2 crests or 2 troughs? 2 troughs, yep. It's exactly between these 2 crests, exactly between these 2 crests. So there's 2 troughs in that location, and that is constructive interference. What if I put a dot right here? Constructive or destructive? Constructive, absolutely. Because we've got a wave crest right there, and we've got another wave crest right there. So 2 crests means constructive interference. How's it going so far? We're almost through the first page of the test, folks. So again, you know, we spend most of our time on the difficult stuff because it's tough. You got to spend more time on it. But that doesn't necessarily mean the test is going to be all that difficult. Just because we spent most of our time figuring out those hard problems doesn't mean the test is going to be entirely hard. We got to have the test that's nice and diverse so that it has the easy stuff and the hard stuff. So try not to worry too much when you see physics tests, because again, you've got easy and hard stuff on the same thing. So this is an interesting one though. Let's say I have a dot right here. What are your thoughts on that? Perhaps destructive, perhaps constructive, maybe neither. That's a good point. And you need that point in order to understand what the answer to this question is going to be. This dot does lie on a maximum line. And what does a maximum line represent? Constructive interference. So because this dot lies on a maximum line, it would also be considered constructive interference. Even if it's not exactly on 2 crests or exactly 2 troughs, any dot along this line is going to be considered constructive interference. That's something that you'll need to know. All of them, yeah. So for this line here too, the line that would pass through these right here, any spot on that line would be constructive interference too, along with any of the other maximum lines. All right. Now let's say that I give you how fast these waves are moving. Maybe they're moving at wave speed of 5 meters per second. And maybe I also tell you that the wavelength, or maybe you measure the wavelength. Maybe I have you measure the wavelength with a straight edge or something. And maybe you measure the wavelength to be 10 meters. Of course, I suppose if it's on the test, that would be like 10 centimeters, because that's an awfully long wavelength for one page. So, if you have your wave speed and you know your wavelength, perhaps I might say, calculate the frequency. Bless you. See what you can do with that. It's also helpful to have your formula sheet out during this because you'll have that during the test. So if you have that on, you feel free to grab it. The equation for this is in the waves box. If you don't have it, it's listed as wave speed equals wavelength times frequency. So what's the answer going to be for this one? 1/2, exactly. Because if wave speed is equal to wavelength times frequency, that means that your frequency is equal to wave speed divided by wavelength. And of course, 5 divided by 10 is equal to 0.5. So your frequency would be 0.5, and what are the units on frequency? Hertz. Yep.
Question.
Yep.
Can we keep it in fraction form or would you like those?
I'd like it in decimal form. In the sciences, we try and stick with decimals. So yeah, this is the sort of thing to expect on page number 1. Page number 2 is going to be basically one big problem. We're going to do one that's very similar to it. So, we've talked a lot about waves, and we've talked a lot about what their amplitude actually is, their frequency, their period, all of that fun stuff. And instead of having you measure these things, on the test I'm going to have you compare them. You'll see what that means in a second here. So we've got 2 waves. We'll call the top one wave A and bottom wave B. Now for this page on the test, you're going to be asked to compare different characteristics of these 2 waves. And the way that you are supposed to answer is this. A is greater than B, A is less than B, and A is equal to B. Those are the 3 answers that you could possibly have when you're comparing their characteristics. So, let's compare some of these characteristics. We can assume both of these waves are moving in the same medium here. So go ahead, see what you can do with this. Compare their frequencies, amplitude, period, wavelength, and wave speed.
does the T stand for then?
Period. It's just a matter of kind of eyeballing it. Like those waves are happening in the same period of time, so you should be able to draw a conclusion about frequency. And then using that, you should be able to figure out period, and the others you can figure out separately. Another 30 seconds and then we'll go through this one. So let's take a look at this then. If we're solving for which of these waves has the greater frequency, what we're really looking for with frequency is, how frequently are these waves passing a certain point? How often do we have a new wave crest occurring? The more frequently we have a new wave, the higher the frequency is going to be. So in which of these waves do we have more bumps? B. The waves are occurring more frequently in letter B. Therefore, it's got a higher frequency. So that one's going to be A is less than B, because B has a larger frequency. And of course, if we know that's what the frequency is, what does that mean for the period? Yeah, exactly. So if we know that A has a smaller frequency than B, that means that A is going to have a larger period than B, because it's that inverse relationship between those two. So A is going to be greater than B for a period. Now A is amplitude. Which one's taller? B. So A is less than B. Which one has a longer wavelength? A. So A is greater than B. Which one's moving faster?
No, they're the same.
How do you know they're the same?
Because the medium's the same.
Exactly, yeah. Yep. So unless it tells you that the medium changes, these waves are going to be traveling the same speed, and it'll say if it's the same medium or not. But yeah, because they're moving in the same medium, it does not matter what they look like or how different they are. They have the exact same wave speed under those conditions.
How come the wavelength is different?
You mean like how would you measure it?
Yeah.
Sure. So you would take your straight edge, and you can get wavelength by measuring crest to crest or trough to trough. So if I'm measuring the distance, it actually lines up pretty good here. That's nice. From this crest The next one, that distance is greater than this right here. And so wavelength of A is going to be greater than the wavelength of B.
Are you gonna have like all that stuff on the red? Like, is that gonna be on the test, and then we'll just have to fill it in?
Yeah, basically. Yep. This is pretty much the exact thing you should kind of expect for page number 2. They won't be the exact same waves, of course. I'm going to change that up. But it's the same questions and the same ways that you should format your answer. And by the time you get done with that page, you're going to be extremely excited because you're halfway finished. All right, on to the sort of thing you'll see on page number 3. So remember when we were dealing with reflection and refraction with waves? That is what page number 3 is going to be about. So maybe you've got this interface here where you've got a barrier and there might be some waves coming in. So they're moving in the direction of the barrier here, and for this kind of a question, you'd be asked to show reflection. And when you show reflection, there's a lot of things that you got to remember to draw in here, and each of these things will be listed on the test. You need to draw in the normal. You need to draw in both rays. The one coming in and then the one leaving. And then any missing wave fronts. The waves coming in were drawn, so then of course you're going to have to draw the wave fronts as they leave. Alright, so if I'm going to do this, the first thing that I would do is I would draw in the missing ray from these waves here. And again, you don't have to line that ray up with the arrows that they give you. You could go something like this. Oh yeah. So that would be my ray. And remember that your rays have to be perpendicular to the wave fronts. That's the main thing you have to remember when you're drawing your rays in here. The next thing I would probably draw is the normal line. That's just the dotted line that's always perpendicular to the surface. So this is our barrier here. It's our change in surface. And so the normal line has to be perpendicular to that. The next thing I would probably do is draw in the reflected ray. So it's going to bounce and go down like this. And I'd want to try and make that angle about the same as this one. So something like this, maybe. So you kind of want this angle to be about the same as that one. And then the final step is drawing in those missing waves. Well, those waves have bigger, smaller, or the same wavelength down here. Same, exactly, because it's the same medium. And it doesn't matter where you draw them, as long as they are perpendicular to the ray. So that would be a totally acceptable answer. And like if you look close, these are probably a little smaller than these. Just eyeball it. It's not going to be the sort of thing where I'm going to try and take points off for them not being the exact right distance. This would be a totally acceptable answer. Questions on this one? All right, let's do refraction now. So the waves are all moving in this direction to the bottom right. And I'll say that the top is going to be our slow medium. And the bottom is our fast medium. And you need to include the same things that we included in the previous example. We need to make sure that we have any missing rays. We need a normal line. And whatever wave fronts that we need to draw. So make sure you have all of those in there. I'll give you a minute or two to see what you can do with this. Just like the previous test, if bringing in a Hot Wheels car helps you with this sort of thing, with the direction of the rays, feel free to do that. You're more than welcome to bring a Hot Wheels car in. It's actually encouraged, I'd say. I'll borrow you one then. I got plenty to go around. Okay, so if I'm doing this one, I see that the ray is already drawn in. It's drawn in very nicely. So I'm cool with that. I don't have to draw in the first ray like I did the last one. But I do want to make sure that I put the normal line in. So that'll be my first step on this problem. Nice and perpendicular. So now I got to figure out what direction this ray, and therefore these waves, are going to take when they go from a slow medium to a fast one. So knowing what you know with the car analogy, is this going to curve down or is it going to curve more across? Across, exactly. Because if we have that car analogy, this might be the very last time you see this. If we use this car analogy and it's coming down like this in the slow medium, now the front right tire is moving faster than the front left. So if this tire is moving faster than the other one, it's going to make the car turn to the side like this and go across. So that's the direction our ray is going to be going. Something like that. And when I put my waves in, how will the wavelengths compare? Bigger or smaller? Bigger, absolutely. Because we're in the fast medium. When we're in a fast medium, the wavelengths are more elongated. In a slow medium, they're more bunched up. So that would be an acceptable answer to this question. What's that? No. We still have like 8 minutes to go. Okay. That's probably the last hard question, though, I'd say. So page 3 is the one where I'd say you really got to buckle down and focus. The others aren't quite as painful. So, remember diffraction? We sent, those waves through a narrow opening. Which of these waves would curve and bend more? The one on the top or the one on the bottom? The top, yeah. Because a longer wavelength makes those waves more easy to diffract, more easy to bend. And if this question was on the test, what I'd be looking for, if I ask you to draw what comes out the other end, I'd be looking for this one to be more curvy than this one. So I can see pretty clearly that this is not curving or bending as much as that one up there. And that distinction is what I'm looking for this. If you see this question, don't draw them the same. Make sure that I can tell which one is bending more than the other. On that same note,
That's diffraction, right?
yep, that's diffraction. On that same note, if I give you a problem that would look like this, yep. Which of these two questions will have a longer, like, shadow behind the barrier here, where the waves are not connected? The bottom one. Because these wavelengths are much closer together. Close together wavelengths have a more difficult time bending, so they'll have a more difficult time reconnecting after that barrier. And this picture should be in your notes somewhere already. But yeah, you have a pretty big area here where the waves are not connected yet. This one, maybe something like this. As long as I can tell that this area is smaller than this area, that's what I'm looking for. And that's page number 3. The final page, this is in addition to the refraction and reflection stuff on page 3. The final page are 3 short answer questions. And I'm basically going to tell you, not exactly what they are. Well, I'll tell you what the first one is. The first question goes like this. Explain in your own words how light behaves as a wave. I'll let you write it down. Explain in your own words how light behaves as a wave. The follow-up, is light a wave or a particle? Again, explain in your own words how light behaves as a wave. And the follow-up is light a wave or a particle? Remind me, is light a wave or a particle? Particle. Light is a particle that behaves like a wave. That's really what I'm looking for to the answer for that second question. Light is a particle that behaves like a wave. And of course, for the first part of that question, that's exactly what you did for your essay. So feel free to reference that. That's where you talk about the maximum lines. Bless you. That's where you talk about diffraction and that sort of thing. So make sure to review for that. The second short answer question, you have to know how wavelength affects diffraction. You have to know how wavelength affects diffraction. I'll give you a second to write that down. Bless you. And then I'll explain what that means. Affects diffraction. And again, diffraction is how, the different colors of light bend when they go through a small opening. So what you have to remember for this one is that when we shot the red laser through the diffraction grating, was that more spread out or less spread out than the green? Exactly. So that's like from the notes that I gave you briefly yesterday, that diffraction and wavelength are directly proportional. The bigger wavelength red light will bend and diffract and be more spread out than the shorter wavelengths. And that brings us to the final question. You have to know how wavelength affects refraction. You have to know how wavelength affects refraction. And that's what we talked about yesterday too. So for that one, you have to know that if light is going through a prism and it gets bent into its separate colors, which color is going to bend the most, the red or the purple? The purple is going to bend the most, because the short wavelengths refract more than the long wavelengths do. If you're looking at a prism, the purple light is going to bend more because those short wavelengths will always change direction more than the red ones do. And that's for refraction. You need to make sure that you know the difference between those two. If you have any other questions or you want to review anything more, feel free to come see me. Feel free to review any of the videos on Schoology. See you tomorrow!